It's really quite something when you stop and think about just how much information we're creating every single day.
It's staggering.
Yeah, I saw this stat. Something like 2.5 quintillion bytes of data daily.
Wow.
And get this, 90% of all the data out there was apparently created in just the last, what, 2 years?
That sounds about right. It's
Yeah.
just exploded.
Makes you wonder, how do we even begin to make sense of all that?
Well, that's the big question, isn't it? And that's really what we're diving into today. This data explosion is a massive opportunity, but, you know, only if you can actually find the valuable stuff in all the noise.
Exactly. And that's why we're doing this deep dive. For anyone listening who wants to sort of get a solid handle on navigating this big data world without getting totally overwhelmed.
Mm.
And our guide here is the book Analytics in a Big Data World, The Essential Guide to Data Science and Its Applications by Bart Basins.
A really practical book.
Yeah, that's the idea. We're not aiming for like a super exhaustive academic review. Think of this more as your shortcut.
Your practical guide.
Right, to the core ideas, the key techniques, how it actually works in practice. Our mission really is just to get you the essentials without drowning in jargon.
So yeah, we'll walk through the whole analytics process, look at some key methods, and importantly, talk about what it takes to actually put analytics to work effectively.
Oh, okay, sounds good. So where do we start? The process itself.
Makes sense. The book lays out a pretty logical flow, a kind of model for the analytics process.
And step one, it sounds almost too simple, but I guess it's critical, defining the business problem.
Absolutely fundamental. You need to know why you're doing the analysis, what question are you trying to answer, what decision are you trying to inform.
You can't just like wander into the data and hope for the best.
Not really, no. You need that focus.
Right.
Once you have that clear problem definition, then you move to identifying and selecting the right data.
Data as the key ingredient, right?
Exactly. It's the fuel.
Mm.
Rubbish data in, rubbish insights out, even with fancy techniques.
Like trying to bake a cake with sand instead of flour just won't work.
Precisely. So you find your relevant data, and then the book talks about gathering it into a staging area. Think like a data mart, maybe a data warehouse.
Okay, what's the point of that extra step? Why not just analyze it directly?
Well, it's like setting up your kitchen before you start cooking. This staging area is a controlled environment. It lets you gather everything in one place, clean it up, maybe do some initial transformations. It just makes the whole process much more organized and efficient.
Ah, okay. The prep station. Got it.
Yeah. And after that, you typically do some basic exploratory analysis. The book mentions OAL, online analytical processing.
OLAP, right. What does that involve, practically?
Imagine you have a big table of sales data. OLAP tools let you slice and dice that data really easily. Look at sales by region, then by product, then over time, all interactively.
So it's like looking at your data cube from different angles.
That's a great analogy. It helps you get a feel for the data, spot obvious patterns, maybe some anomalies before you dive deeper.
Okay. And then comes the bit that's maybe less exciting, but totally necessary. Data cleaning.
Oh yeah, the grunt work. Dealing with missing values, weird outliers, duplicate records.
Sounds messy.
It can be, but if you don't do it, all those inconsistencies and errors, they just introduce noise, maybe bias, into your analysis. Your results won't be reliable.
So cleaning is non-negotiable.
Pretty much. Then, after cleaning, you often need to do some data transformation.
Transforming? Like what?
Well, maybe you group a continuous variable, like age, into bins, 20, 30, 31, 40, etc. Or you might need to convert categorical things like yes, no, into numbers like 1 and 0, so the algorithms can understand them.
So shaping the data for the tools you're going to use.
Exactly. Getting it into the right format. And then finally, you get to apply the analytical models.
This is the part everyone thinks of, right? Predicting things.
Yeah. The book gives great examples. Predicting customer churn who's likely to leave, detecting fraud, segmenting customers into groups. Or that classic one, market basket analysis, figuring out what people buy together.
The diapers and beer example.
That's the one. Though maybe a bit dated now. But yeah, these models answer those kinds of questions.
But it doesn't stop there, does it? The model gives an answer, but...
Right. Interpretation is key.
Right.
Business experts need to look at the results. Do they make sense? Are they useful? The book calls it searching for knowledge diamonds.
Knowledge diamonds. I like that.
Yeah, those unexpected insights, the actionable patterns that can actually lead to better decisions. It's not just about the math, it's about the meaning.
Finding those nuggets. And the final step.
Deployment. Turning that model into a working application. Maybe it becomes part of a decision support system running in the background, helping make real-time choices.
Embedding the insight into the workflow.
Exactly. Now, a really crucial point the book makes is that analytics isn't a one-person show.
Right, it takes a village, or at least a team.
It's multidisciplinary. They talk about key roles. First up, the database or data warehouse admin, the DBA.
The folks who actually manage the data infrastructure.
Yep, absolutely vital. They provide the clean, accessible data you need. Can't do much without them.
Unsung heroes, maybe.
Often, yeah. And then, increasingly important, legal experts.
Because of privacy and fairness concerns.
Exactly. Privacy regulations are getting stricter everywhere, and you have to worry about discrimination. Like in credit scoring, you can't use race or religion.
Or gender or origin.
Right.
Okay.
And online, think about cookies and tracking the rules are complex and vary by location. You need legal guidance to navigate that.
Makes sense. Avoid stepping on any landmines.
Definitely. And then, of course, you have the people actually building the models, the analysts, the data scientists.
The book mentions all these related terms: analytics, data science, data mining, knowledge discovery. Sounds a bit confusing.
Yeah, the lines can be blurry, and people sometimes use them interchangeably. But the core goal is the same. Find patterns, extract insights, build predictive models from data. That's the common thread.
And they pull techniques from all over, don't they?
Oh, yeah. Statistics, obviously. Machine learning, which comes out of computer science. Even ideas inspired by biology, like neural networks. And math-heavy stuff like Kerner methods. It's a real melting pot.
A mix of skills needed. And the impact, especially in areas like finance. The book really highlights how much banks rely on these models for risk decisions.
Huge reliance. Credit risk, market risk, operational risk, fraud, insurance. Analytical models are central to managing these.
Which means, if the model is wrong,
the consequences can be massive. Financial losses, reputational damage. It underscores why doing analytics properly, rigorously, is so critical.
Which is a perfect lead-in to thinking more about the data itself. Chapter 2 gets into data quality and pre-processing. Sampling comes up first.
Right. And it's not always simple. Sampling bias is a real risk.
How so?
Well, take that credit scoring example again. If you only build your model using data from people whose loans were approved, you're ignoring everyone who was rejected.
The through-the-door population, they call it.
Exactly. But you don't know how those rejected people would have actually performed. Your model might be biased because it's only seen the good risks, potentially. Trying to infer the performance of the rejects is tricky.
So your sample isn't truly representative.
It might not be. That's why techniques like stratified sampling are important, especially for skewed data sets.
Skewed. Like when you're looking for something rare.
Yeah, like customer churn or fraud. Often, only a tiny percentage of your data represents those events. If you just take a random sample, you might barely get any examples of churn or fraud to learn from.
So stratified sampling makes sure you get enough of the minority group.
Precisely. It ensures your sample preserves the proportions of important subgroups, giving the model a fair chance to learn about them.
Okay. Then they talk about different types of data elements.
Yeah, the basic types. Binary, just two values, yes or no, none, one, all. Categorical distinct groups like product types or colors. These can be nominal, no inherent order, or ordinal, like low, medium, high.
And continuous data.
Numerical data you can measure. Income, temperature, age. Subdivided into interval and ratio scales, though the distinction isn't always critical for basic modeling.
And the key point is you have to tell your software what type each variable is.
Right. Absolutely crucial. If you tell your tool that marital status is a continuous number and it tries to calculate an average, well, that's meaningless. Utter garbage.
Right. Different tools handle data types differently.
Exactly. They also briefly mention visual exploration charts, graphs, and basic stats, just to, get your eyes on the data first.
Always a good idea. And then, missing values again. They seem unavoidable.
They really are. Data might be missing because a question wasn't applicable, or someone just didn't answer, or maybe there was a system glitch. Lots of reasons.
So how do you deal with them?
Well, some algorithms can handle them internally, but often you need to do something. A common approach is imputation replacing the missing value.
Like with the average value for that variable.
Yeah, or the median, or the mode, most frequent value. You can also use more complex regression-based methods to predict the missing value based on other variables.
Does that complexity help much?
The book is actually a bit skeptical, suggesting the fancy methods often don't add that much value in practice compared to simpler ones, which is interesting.
Simpler is sometimes better. What about just deleting the data?
That's another option, especially if a whole record or variable has tons of missing values. but you have to be careful. You should only really do that if you think the missingness itself is random and doesn't contain information.
What do you mean contain information?
Sometimes why data is missing is important. Like, if someone applying for a loan deliberately doesn't state their income,
Yeah.
that might tell you something.
Oh, okay. So maybe missing should be treated as its own category sometimes.
Exactly. Or you could even run a statistical test to see if missingness on one variable is related to your target outcome. Don't just throw potentially useful info away.
Good point. Then outliers, those extreme values.
Yep. They can be valid, like a genuinely super high income, or invalid, probably due to a typo or error. And outliers can be univariate, extreme on one variable, or multivariate. Weird when you look at multiple variables together, like someone who is 5 years old and has a PhD.
Right. How do you spot them?
Simple things first. Check minimums and maximums. Look at histograms. Outliers often appear as isolated bars far from the main distribution.
You can literally see them sticking out, and once you find them.
Well, you need to decide if they're errors to be corrected or genuine extremes to potentially handle differently. Standardization techniques come up here too.
Like min-max scaling or z-scores.
Yeah. These rescale variables to a common range, which helps some algorithms, like regression or anything distance-based, where variables with huge values might otherwise dominate.
But not always needed.
The book notes they might not be necessary for models like decision trees, which aren't as sensitive to the absolute scale of the inputs.
Okay. And then categorization or binning, grouping values together.
Right. You might do this for categorical variables, if you have way too many categories, grouping smaller ones into an other category perhaps.
Makes the model simpler?
Simpler and often more stable. And you also bin continuous variables sometimes.
Why would you do that? Doesn't that lose information?
It can, but it allows simpler models like linear regression to capture nonlinear effects.
Right.
Imagine income versus likelihood to buy. Maybe the likelihood jumps up at certain income thresholds. Binning lets a linear model approximate that stepped relationship.
I see. Assigning different weights to different income bins.
Exactly. The book mentions basic binning versus more sophisticated methods like using chi-squared analysis to find optimal bins, or something called weight of evidence coding.
Weight of evidence, WOE. What's that about?
WOA is a way to transform each category of a predictor into a single number that reflects how much the odds of the target outcome, like good versus bad customer, differ for that category compared to the overall odds. It often creates a nice monotonic relationship with the target, which is great for logistic regression.
Interesting. Sounds quite powerful. And finally, in this section, variable selection.
Yeah, especially if you start with hundreds or thousands of potential predictors, you need ways to filter down to the most useful ones.
How do you filter?
They discuss filter measures, which look at each variable individually. Chi-squared analysis, like we mentioned for binning, can be used, and specifically, Kramer's V.
Kramer's V.
It's a measure derived from chi-squared that tells you the strength of association between two categorical variables. It goes from 0 to 1. You might set a threshold, say 0.1, and only keep variables with a Kramer's V above that.
As an initial screening tool.
Exactly. But it's univariate. It doesn't account for interactions between variables, so it's usually just a first step. More selection happens during modeling.
And it's not just stats, right?
Yeah.
Other factors matter.
Definitely. Regulatory compliance is huge. We mentioned anti-discrimination laws. You can't use protected characteristics, even if they seem statistically predictive.
Even indirectly.
Yes, you have to be careful about proxies too. And then there are practical, operational issues. Is the variable easy and cheap to get? Is it available quickly enough for the decision you need to make?
Right. A super predictive variable is useless if it takes weeks to collect for a real-time decision.
Exactly. Lots of trade-offs to consider.
Okay, so data prepped, variable selected. Now we're really into the predictive modeling itself in Chapter 3.
Yeah, this is where we build models to actually predict a target variable.
And first things first, defining that target variable properly needs to be robust, stable.
Absolutely. If your definition of churn or default keeps changing, your model's predictions become meaningless. They mention roll rate analysis and credit scoring as a way to get a stable definition of delinquency over time.
And they introduce some key target examples like customer lifetime value, CLV.
Right, CLV is a big one for marketing. It's a continuous variable predicting the total net profit you expect from a customer over their entire relationship with you. It involves estimating future purchases, costs, retention probabilities. Quite complex.
Needs input from finance and marketing, for sure.
Definitely. And for credit risk, another key continuous target is loss given default, or LGD, predicting how much you'd lose if a borrower defaults.
Okay. So once you have your target, what techniques do you use? They start with the basics. Linear regression.
Yep. Good old linear regression. Great baseline for predicting continuous targets like CLV. You model the target as a linear combination of your predictor variables, maybe using RFM metrics, recency, frequency, monetary value.
Simple, interpretable. You see how each factor contributes.
Exactly. But what about binary targets? Yes, no churn, fraud, no fraud.
That's where logistic regression comes in.
Right. Because linear regression can predict values below 0 or above 1, which doesn't make sense for a probability. Logistic regression uses a sigmoid function, or a similar squashing function.
To map the output between 0 and 1.
Precisely. It models the log odds of the event happening as a linear function of the predictors, and the results can be interpreted using odds ratios, which is quite intuitive. It essentially finds a linear boundary, but in that log odds space.
Okay. Then decision trees. These seem more visual.
Very intuitive. They work by splitting the data repeatedly based on rules, like if income $50, go left, else go right. Then within the left branch, if age 30, go left, and so on.
Creating a tree structure, how does it decide where to split?
It uses impurity measures, like DeMarty index or entropy. It looks for splits that make the resulting groups purer, meaning more dominated by one outcome class than the other.
And it keeps splitting until, when does it stop?
Good question. If you let it split too much, it overfits, it basically memorizes the training data, noise and all, and won't generalize to new data. So you need stopping criteria. Often involves using a separate validation data set to see when performance on unseen data starts to degrade.
Makes sense. Use unseen data to check generalization.
Right. And trees are great because you can easily read off the rules from the path down a branch. If income 50K and age 30, then predict churn. Very transparent. They call them white box models.
That interpretability is a big plus, unlike, perhaps, neural networks.
Well, neural networks can be harder to interpret, yeah? They're inspired by the brain with layers of interconnected nodes or neurons. They're powerful for finding really complex, nonlinear patterns.
The book links them back to simpler models too, right? Like logistic regression is a one neuron network.
Yeah, that's a helpful way to think about it. A typical network, a multi-layer perceptron, MLP, has input nodes, one or more hidden layers, and output nodes. Those hidden layers are where the complex feature learning happens.
How do they learn?
Through an iterative process. You feed data through, compare the network's output to the actual target, calculate an error, and then adjust the connection weights slightly to reduce that error. Repeat thousands of times.
Sounds computationally intensive.
They can be, and like trees, they can overfit if you're not careful. Using validation sets, techniques like regularization to penalize large weights, these help control overfitting. But their power is undeniable for certain problems.
But often called black boxes.
Yeah, because figuring out exactly why it made a specific prediction by tracing through all those weighted connections is really difficult. Though the book mentions techniques trying to extract rules or combine them with simpler models to get some interpretability back.
Interesting. Okay, next up. Support vector machines, SVMs. What problem do they solve?
SVMs offer a different approach, particularly for classification. They try to find the best separating hyperplane. Think of a line in 2D, or a plane in 3D between classes. Best means maximizing the margin, the gap between the hyperplane and the closest data points of each class.
Maximizing the buffer zone.
Exactly. And if the data isn't perfectly separable, it allows for some errors using a parameter C to control the trade-off between a wide margin and misclassifying fewer points.
What if a straight line just won't work to separate the classes?
That's where the kernel trick comes in. SVMs can use kernel functions like polynomial or radial basis function, RBF kernels, to implicitly map the data to a higher dimensional space where separation is possible with a hyperplane.
Clever. Mapping it to a space where it becomes linear.
Yeah. And interestingly, an RBF SVM can be shown to be equivalent to a specific type of neural network, where the number of hidden units is determined by the support vectors, those critical data points near the margin. SVMs can also be adapted for regression.
Lots of options. Then ensemble methods. Combining models.
Right. The idea is that a team of models often performs better than any single model. Two main types are discussed, bagging and boosting.
Bagging. Like bootstrap aggregating.
Yep. You create multiple versions of your training data by bootstrapping, sampling with replacement. Train a separate model on each bootstrap sample. Then for a new prediction, you just average the predictions of all the models for regression or take a majority vote for classification. Random forests are a popular example of bagging with decision trees.
Reduces variance, makes the prediction more stable.
Generally, yes. Then there's boosting, like AdaBoost.
How does that work?
It's sequential. You train a simple model, a weak learner, then you look at its errors, you increase the weight of the misclassified examples, and train a second weak learner, forcing it to focus on the mistakes of the first one. You repeat this, weighting each model's vote based on its accuracy.
So it iteratively focuses on the hard-to-classify cases.
Exactly. Boosting can be extremely powerful, often yielding very accurate models, but it can also be sensitive to noisy data and potentially overfit if you boost for too long.
Trade-offs everywhere. The chapter also quickly covers multi-class problems.
Yeah, extending these ideas beyond just two classes. Logistic regression, trees, neural networks, SVMs, they all have multi-class versions or strategies like one versus all or one versus one for SVMs.
Okay, so we've built a model. Now, crucially, how do we know if it's any good? Evaluation.
Absolutely critical.
Ugh.
For binary classification, the starting point is the confusion matrix.
True positives, true negatives, false negatives.
Right. It lays out the 4 possible outcomes. From that, you calculate key metrics. Accuracy is the simplest overall percentage correct. But it can be misleading if your classes are imbalanced.
Like in fraud detection, where 99.9% accuracy might sound good, but if you miss all the rare fraud cases.
Exactly. So you look at precision of the positive predictions, how many were correct, and recall or sensitivity of the actual positive cases, how many did you find? And the F1 score, which combines precision and recall.
What about the ROC curve?
Receiver operating characteristic, very important. It plots the true positive rate, recall, against the false positive rate, one specificity, at various classification thresholds.
Showing the trade-off between catching positives and avoiding false alarms.
Precisely. The area under the ROC curve, the AUC, summarizes this. AUC is between 0.5, random guessing, and 1, perfect classifier. It's a widely used measure of overall discrimination ability. The book gives some benchmarks for what's considered good AUC in practice.
And lift curves.
Lift helps you see how much better your model is than random guessing at concentrated the positive cases in a top portion of your ranked list. Useful for marketing campaigns, for example.
And for regression models predicting numbers.
You use error metrics like mean squared error, MSE, root mean squared error, RMSE, mean absolute error, MAE, basically measuring the average difference between predicted and actual values, and R squared, which tells you the proportion of the target variable's variance explained by the model.
Okay, a whole toolkit for evaluation. So let's say we've built and evaluated a decent model. How do we actually use it effectively? Chapter 7, putting analytics to work.
Right. Building the model is often just the beginning. The book lists key requirements for models in practice, and statistical performance is only one of them.
What else matters?
Business relevance, does it solve a real problem? Interpretability, can we understand why it makes certain predictions? Operational efficiency, can we actually run it easily? Economical cost, are the benefits worth the cost? And regulatory compliance.
That balancing act again, what's important depends on the context.
Totally. Then backtesting. Checking if the model still works over time.
Because the world changes, right?
Exactly. You compare predictions made earlier with what actually happened later. But it's tricky. You have to account for random sample variation, external shocks like economic downturns, or internal changes like new company strategies.
How do you monitor stability?
They mention metrics like the Population Stability Index, PSI. It measures if the distribution of your model scores, or even key input variables, using the Variable Stability Index, VSI, has shifted significantly over time compared to when the model was built.
A warning sign that the model might be going stale?
Precisely. You also track performance metrics like accuracy ratio, or AUC, over time, and check if the model's predicted probabilities are still well calibrated using things like the Breyer score. It's about having a framework for ongoing monitoring and action.
Continuous vigilance and benchmarking. Comparing your model to others.
Yeah, comparing it to maybe an external standard like a FICO score in credit or an older internal model helps you gauge relative performance and see if you're actually improving. Statistics like Spearman's rank correlation can measure agreement between your model's rankings and the benchmarks.
Gives you context, then data quality again.
Can't emphasize it enough. Fitness for use. Is the data accurate, complete, consistent, timely? The book lists several dimensions and reiterates. Garbage in, garbage out. Ongoing data quality management is crucial.
And privacy, a huge topic now.
Definitely. Analytics raises new privacy concerns because you can discover hidden patterns people might not even know about themselves. The book mentions core principles like the Fair Information Practice Principles, FEPPs, which inspire many laws. Things like notice, choice, access, security.
And it touches on privacy-preserving techniques.
Briefly, Methods like anonymization, generalization, suppression, or adding noise perturbation that try to let you analyze data while protecting individual identities. It's a complex and evolving area.
A very tricky balance. What about documenting the model?
Hugely important, often overlooked. You need thorough documentation covering the design, the data used, the assumptions made, strengths, weaknesses, how it was tested, everything. Someone else should be able to understand and potentially replicate your work.
Aiming for a documentation test, could someone else pick this up?
That's a good way to put it. And finally, corporate governance.
Making analytics part of the business structure.
Yeah. Clear ownership, who is responsible for the model, maybe a model review board, senior management and board involvement, even the idea of a chief analytics officer, CAO, to champion analytics strategically.
Embedding it properly within the organization.
Exactly. It needs that high-level support and structure to really thrive.
Wow. Okay, that was a really comprehensive tour through analytics in a big data world. We've gone from the basic process through data prep, key modeling techniques, evaluation, and all the way to making it work in the real world.
It covers a lot of ground. And hopefully it highlights that while the techniques are fascinating, success really depends on understanding the business context, having good data, and being thoughtful about implementation and ongoing monitoring.
Yeah, it's much more than just running algorithms.
Definitely. And this field changes so fast, there's always more to learn. Hopefully this deep dive gave everyone a solid foundation and maybe sparked some interest in digging deeper into specific areas we touched on.
Absolutely. And as we're all trying to make sense of this, flood of data we're living in, being able to analyze it effectively, it feels less like just a business advantage now and more like a fundamental skill.
A way of understanding the world.
Yeah. It makes you think, with all this data and these powerful tools, what new knowledge diamonds are out there waiting to be uncovered by you?